First of all, I would like to acknowledge Ministry of Earth Sciences, Director IITM, and the Golden Jubilee Award Committee, and all my colleagues. So I'll be talking on the role of atmospheric aerosols on cloud microphysics and precipitation. And the traditional view of aerosol sources are mainly some are natural. For example, from ocean we can get sea salt, and from vegetation we can get organic aerosols through conversion of volatile organic compounds into very fine particulates. And from land use, land changes, we can get the dust aerosols. And from industrial emissions and biomass burning emissions, we can get sulfate, soot, and organics. So these are the traditional view of aerosols, and they influence the climate through different ways. One is that what you see here is simple scattering and absorption. So it can reduce the incoming solar radiation, and in turn it can partially offset the greenhouse warming. Then this is relatively now well understood in spite of the complex composition of aerosols, different types of aerosols. But the effects of aerosols on cloud and precipitation is still not very well understood. And if you see this schematic, so the unpolluted cloud or pristine clouds can have very few number of larger droplets. So whereas in polluted conditions, so for a given liquid water content, we'll have more number of smaller droplets. So that will increase the reflectivity of the cloud. For example, if you see for the same volume, if there are more droplets, then you have you are increasing the reflective surface area. Okay, so which increases the albedo of the clouds. Then other process is when the droplets are more and it is small. So then it can also affect the warm rain initiation, because generally the cloud droplets precipitate when they are colliding and coalescing. But if there are droplet size is small, then what you see is, so it can pass through the streamlines and without colliding the larger drop, so it can escape. So the collision coalescence efficiency gets suppressed. So that's what, see, the adding more number of aerosols in the atmosphere suppresses the warm rain initiation process. There are several other effects when the aerosols are of absorbing type. So it can increase the heating in the atmospheric layer so that it can reduce the cloud cover. Also, when the clouds can grow deeper, and it can lead to cold rain processes. So we can get into heavy rain events. So there are several effects, and still if you look at the IPCC report, so we have the level of confidence is still low in terms of the effect of aerosols on clouds and precipitation. Whereas if you see the direct effect, for example, the scattering and absorption, and in turn the cooling of the surface, which is relatively well understood, so our level of confidence is high. So the fundamental cloud microphysical properties are driven by dynamics, and the vertical motions and mixing processes between the cloud and environment determine the concentration of cloud water, which is a key parameter for both climate and precipitation. However, aerosol particles can significantly affect the microphysics and dynamics by changing the size distribution of drops, their ability to grow to raindrops, their rates of evaporation, and their mixing with the environment. So as these are thrust areas, IITM implemented a focused project called Physics and Dynamics of Tropical Clouds, under which the process studies are undertaken, which could help tuning and improving the cloud microphysics parameterization schemes. So now the previous speaker has given the effect of topography. So I'm coming to the orographic precipitation. So we have implemented some aircraft observation, which my colleague will subsequently talk. So in addition to aircraft measurements, we also thought to get a long-term interactions between cloud and aerosols. We have established a cloud physics laboratory in Western Ghats. because it's a natural laboratory wherein warm clouds float close to surface and interact with the surface aerosols, which can be monitored to understand the role of aerosol physical and chemical processes on the microphysics of clouds and precipitation. Orographic precipitation, which is a source for hydrological cycle, is showing a decreasing trend. For example, if you look at this, so if you look at the trend for last 100 years, so there is a decreasing trend in last 2-3 decades. So there are several possible players, but so one could be the increase in anthropogenic emissions and change in land use land cover, which can play a major role in modifying the microphysics of clouds and precipitation. So it is important to note that the role microphysical and dynamical processes play in the water cycle is still not very clear. So this is the topography of the Western Ghats where the laboratory is situated, and so this is the overall view of the Western Ghats. So mainly the rainfall in this region is coming mainly from shallow clouds, and I invite you, all of you, whenever you go to Mahabaleshwar for any vacation or something, you can stop by and look at our laboratory and the radar facility. So it is a panoramic view of our cloud physics lab, wherein all cloud, aerosol and precipitation processes are measured. So with these following objectives, we initiated this project a few years back, and we started getting good results now. So I'll show you some of the results now. So these are the major objectives. So we make both in situ measurements and remote sensing measurements through radars, and look at how the physical and chemical processes influences the cloud processes and precipitation processes. I'll just browse through some of the facilities. Advanced measurement facilities were implemented in this laboratory. So we have from cloud microphysics instruments and aerosol instruments, and also several cloud processes instruments. This is a site wherein we have both cloud and precipitation radar is established, which is about 25 km from Mahabaleshwar. So it's another hillock. So it's about 1300 meters above sea level. So these are the facilities for both aerosols, clouds and precipitation. So we have been implementing in phase wise, and still there we are yet to implement some of the advanced facilities like volatile organic compound measurements or hygroscopicity of particulates. So for the newcomers, I'll just want to show this is the type of size distribution you will see in the aerosols. So you can see almost there are 4 modes. So this is the coarse mode where sea salt and dust aerosols can come. They are less in number, but it can even the lifetime also is very short. Then we have accumulation mode, IITM mode. There are some nucleation mode, which is generally gas to particle conversion processes, and it adds the particles into the atmosphere. So this cloud condensation nuclei and ice nuclei are subset of these aerosols. So from our observations we looked at, and we see different seasonal patterns. So if you look at the monsoon season, so you have a different diurnal pattern, whereas in other dry seasons we have a different diurnal pattern. So aerosols are highly varying. That's a tough task. It's a highly variable, and also it has different types of diurnal variations. So we were wondering, like, in spite of despite the heavy rain processes in Western Ghats, still there is emission. There are aerosols observed during the forenoon hours. So we want to look at what is the chemistry of these aerosols, and we could see that there are the organics and sulfates, so mainly dominant, and there are other particles like nitrate, chloride, and ammonia. So again, we looked at even in organics, so we can see whether it is secondary organic or oxygenated organic aerosols, or it is from biofuel emissions or biomass burning emissions. So the chemistry shows that the organics is dominant more than 60% over this region. So even though the loading is less, So overall, the mass loading is less because the coarser particles will not be seen in the monsoon season because it gets scavenged, whereas the fine particulates which can get formed in the atmosphere through several processes. I will come into this in subsequently. So this is the type of chemistry, thanks to advanced measurement facilities, to get the detailed chemistry of these particulates. And again, each of these chemical species also has a different diurnal pattern. For example, the organics has different diurnal pattern in different seasons. So, and these are all either the regional influence from the Western Ghats, because in monsoon they have the people, the region uses biofuel, so which adds the organic particulates, and there are the westerlies are strong, southwesterly, so you get the chloride and sulfate aerosols also. So we try to see the source apportionment, so how these, what are the possible sources in different seasons. So for example, if you look at monsoon, so the local sources or in that region, what people use, so that appears to be very dominant. Whereas in dry seasons, you can have a long-range transport also, regional and long-range transport. So this is one of the volatile organic compound. It gets emitted from the vegetation. So Western Ghats has a very dense evergreen vegetation, so that also, so when it is under stress in the dry season or summer, so it also emits isoprene, so which also can get oxidized and get converted into secondary organic aerosols, so which also coincides with the morning peak, in the noon peak. So then the next, we try to see when we are looking at how these aerosols are affecting the cloud microphysics. So we can see here when there are high cloud condensation nuclei, so it implies that you have higher cloud droplet number concentration. So when there are higher droplet number concentration, the effective diameter of the droplets gets reduced, so which in turn can put the cloud into more reflective. So also when the droplets are getting smaller, so it can also suppress the warm rain efficiency. So these are some of the results, and this is the first time we could demonstrate that. So if you try to estimate the indirect effect through either number concentration, droplet number concentration, or how the droplet size are reduced, so we were seeing a large difference in different liquid water content of clouds. So we try to see like what could be the possible reason. So increase in CCM not only increases the droplet number concentration, it can also alter the droplet size distribution. The relative dispersion is a parameter which coming from the droplet size distribution shape. So I will subsequently show. So if we can remove this offset, so then we could see the number and size which we derive from the indirect effect, so which are found to be closer. This is one of the aircraft experiments also was showing. So in the polluted continental region, so you can see how the droplet spectrum is narrow. So whereas when you go to marine coastal regions, so even at a lower depths, the cloud drop size distributions can get broadened. So here we can clearly see that there is a suppression of warm rain initiation, and if we have to really, the warm rain initiation has to initiate, the cloud depth has to further grow. So this is one of the effect of aerosol pollution into the precipitation processes. So we also try to look at what is the role of aerosols into monsoon clouds. So if you look at the average seasonal diurnal variation of cloud condensation nuclei or the integrated cloud liquid, so we could see a different pattern. So this is the rain intensity, observed rain intensity over the site, and you can see there is a effect of aerosols could be seen in the precipitation, but still it needs to be explored further. So we try to estimate the precipitation susceptibility in different liquid water content regimes. So, and we also try to see using the satellite data whether how good the ground measurements are and how the satellite retrievals are, how good they are. So almost both of them are showing that the precipitation susceptibility starts showing increase in the medium liquid water content. Then afterwards, when there is a higher liquid water content, anyway the clouds are going to precipitate. So it's not, the aerosols are not going to play much role because the dynamics are going to take over, and the very high liquid water content, anyway the clouds are precipitate. And the idea of getting such data is to see that whether we can improve the parameterization schemes or whether we can predict the CCN for given the aerosol concentration. So we try to see by using the size and number concentration and the chemistry informations how good we could model the CCN with a given observation, so it could be parameterized. So when we consider different chemical composition, so we could see when we include the oxygenated organic aerosols and inorganic aerosols, the fit between the measured CCN and the estimated CCN are getting better. So this shows that we have to consider the oxygenated organic aerosols. So in future we are planning to have volatile organic compound measurements and trying to estimate what is the role of secondary organic aerosols in this. So in addition to that, as I said, there are several processes which can take place even in the wet season. So one of the processes is new particle formation processes, so which shows there are condensable gases in the atmosphere. When the atmosphere is conducive, so it can lead to secondary particle generation, so which also can contribute to cloud condensation nuclei, and indirectly it can affect the cloud microphysics and precipitation. So these are some of the events. You can see that there is a sudden burst of particles. So when the relative humidity is, the conducive conditions, what we notice is when the relative humidity is low, so we could see that there is a new particle formation which enhances the CCN concentration to a factor of 1.5. Also, we try to see the observatory is in the high altitude, about 1400 meter. So sometimes the site comes into free troposphere and sometimes it is in the boundary layer. So how these free troposphere and boundary layer influences the new particle formation. So we could see that when the site is in free troposphere, we have many nucleation, new particle formation events, so which can enhance the cloud condensation nuclei. When the site is in the boundary layer influence is much, then we don't see such a new particle formation events. The other thing is that, so we try to see that what is the fraction of ice nucleating particle concentration over Western Ghats. So even though the major portion of the rain is coming from warm rains, but still there is a significant contribution coming from cold rain also. So we try to estimate the ice nucleating particle concentration at different temperatures, starting from minus 25 degrees Celsius to minus 34 degrees Celsius with the RH water. Water RH is about 102%. So this is some recent data sets were showing the concentration is about 6 particles per liter, and it shows very good. And we try to utilize the observations into compare with the existing parameterization schemes which are used in the numerical models, and we could see the earlier old schemes are showing high the ice nuclei concentrations. So whereas the latest one from DMOT shows so slightly lower, and it's anyway that the observations are at different places. So these observations, what they have shown is from where the dust aerosols are dominant. So that could be one of the reasons for higher ice nucleating particles present there. Whereas in Western Ghats, so we don't have in monsoon season or in this season, so we have very less ice nucleating particles. So we try to improve with the given measured aerosol concentrations. We are trying to improve the ice nucleation parameterization schemes. So these are some of the cloud radar scans. So we try to scan the clouds and precipitation processes the precipitation radar can see up to 125 kilometer, and the cloud radar can see about 25 kilometer radius. So the cloud radars also were being used to understand the cloud processes and dynamic processes. So these are some of the recent works that how the radar captures from the cloud droplet to rain droplet reflectivity. And if you look at in an active day, summer monsoon active day, so what you see some discontinuities is that radar is doing the vertical measurements, and also it does the azimuthal scanning. So only the vertical scans are combined here, and you can see these are the vertical velocities derived from the radar. And so you can see all the different clouds. So these are some of the cloud radar first measurements over this region, and we try to see so what is the large scale dynamic influence on the bright band. So generally in the radar terminology, the bright band is where the cloud and ice and water transition takes. So that gives a higher reflectivity in radar. So it's called broadband, and we try to see how these broadband gets the width of the broadband, what happens to the width of the broadband in different raining conditions. These are some of the recent results, and we try to look at the different cloud types during different phases of monsoon. So this shows in different 3 different phases from break, transition, and active period. So there is a distinct identity of 3 intraseasonal phases are confined with an altitude of 3 kilometer, and you can see the cirrus clouds in the break periods. And enhancement of cloud water up to an altitude of 3 kilometer can give rise to transformation from break phase to active phases. And so these are this schematic shows the aerosol cloud precipitation related processes which occurs within a typical GCM grid box. So here the blue letters are, these are primary processes, the aerosols, and depends on size and the dynamics, it can get activated as a cloud droplet, and the new particle formation processes and ice formation. So these are some of the primary processes. What is shown in the gray color are the secondary processes and the effects. So this is from the IPCC AR5. To summarize, so I can say clouds are responding to aerosol in a manner that is strongly dependent on meteorological context. Clouds are dynamic entities that are influenced by meteorological factors which control convection. And aerosol particles are a necessary ingredient for cloud droplet formation, but are not the primary driver for clouds. However, they can modify cloud microphysics in sometimes subtle ways to generate feedbacks that may amplify or dampen their influence. So these feedbacks have the potential to make aerosol effects on clouds of major climatic and hydrological importance. So thank you for attention.